So kinetic molecular theory. I don't remember how much we talked about this last year. I feel like not very much, because I think we got into gas stoichiometry and then we were running out of time, so I didn't really have a lot of time to cover this last year. But it's not all that difficult. You know the gas particles move, right? Yeah, okay, so we're good. That's basically it. Gas particles move, and they move a lot, and they move in random motion, yeah. And they hit stuff when they move. Yeah. So one of the things you have to realize, and I think maybe we talked about this when we talked about the ideal gas law last year. I can't remember. There are some assumptions the kinetic molecular theory makes. One of the assumptions is that the volume of the actual gas molecules doesn't matter when you consider the size of the container. Okay. So in other words, you measure the volume of the size of this room, and you add up the individual volumes of all the gas particles in this room, you can essentially just assume that it's zero compared to the size of this room. Does that make sense? Because the gas particles are so small, there's so much empty space in between each of the gas particles that if you added all of those volumes up, they really wouldn't matter for all practical purposes. Now, is that exactly true? No. I mean, they have some volume, right? But we can make the assumption, it simplifies our math quite a bit if we make the assumption that these gas particles don't have any volume, okay? Because all of the gas law problems that we do that involve volume, we are making the assumption in those gas law problems that the gases themselves are not taking up any space, okay? Which is a little weird, but that's the assumption. We also assume that gases aren't attracted or repelled by one another. So these gas molecules are flying past each other, and we assume they're moving fast enough and they're spread out far enough that they really don't experience any attractive or repulsive force from one another, okay? Again, that's a fine assumption under normal conditions, right? When would these two things start to break down, these two assumptions? Under what conditions? Okay, when it's really cold, and then there's another one. Well, not when it's really, actually when it's really hot, this works really well. A lot of pressure, right? So if it's really cold and you squeeze these things into a small area, now all of a sudden the volume of each individual gas particle does matter relative to the small space that it's in, okay? And you've got them close enough to one another and moving slow enough that maybe they actually are attracted to each other a little bit, okay? So that's under normal conditions, like in this room at room temperature, 1 atmosphere of pressure, these are good assumptions. And we can use the ideal gas laws and they work just fine. But if you're, if you're talking about the compressed gas in a cylinder, something like that, they start to not work very well. Okay, so energy can be transferred between molecules during collisions, but the average kinetic energy doesn't change over time as long as the temperature of the gas remains constant. So that makes the assumption that collisions are completely elastic. And you guys haven't had physics, have you? Either of you? Okay. Elastic collisions, so that's like you hit a pool ball on a pool table. The cue ball hits another ball and transfers all of its energy to that other ball. Okay? But that doesn't really happen because there's friction in real life. So these two things hit each other, and some of that energy is lost as heat. Okay? That's what happens anytime two particles really hit each other. But, again, the kinetic molecular theory ignores that energy that's lost during a collision. It assumes that it's all perfectly transferred. Okay? So, again, all of these assumptions are fine for most of our calculations, but they're not perfect. Okay? And then the average kinetic energy of the molecules is proportional to the absolute temperature. We've already talked about that. In the Kelvin scale, temperature is the average kinetic energy of the molecules. Okay. Now this you haven't seen. This is a it's called a Boltzmann diagram or Maxwell-Boltzmann distribution. And your book doesn't call it that, but the AP curriculum does. So I'm going to use that terminology. And when you first look at this, it's like, what is this telling me? Okay. Or at least it was that way for me. If you've got a gas at 0 degrees Celsius, it's saying that the majority of the particles are right here as far as their molecular speed, okay? Now there are some particles over here, and there are some particles over here. But if you take the average, this is probably about the average right here. Okay, this is the vast majority of the particles are there. If you heat up the gas to 100, from 0 to 100, now the particles on average are right here. Okay? Now, see, I drew my averages a little bit different. I guess they're going with the actual mathematical average here, which is not right at the peak necessarily because one side may be wider than the other side. Okay? But notice, on average, now the gas particles are moving at a faster speed. Okay? But the other thing that happens to this is you heat up a gas, now it's got more particles that are moving slower and more particles that are moving faster than that average speed. The curve sort of widens a little bit. Okay? The colder you get, the more the curve narrows. Okay? So if you're over here, you're going to have an even narrower distribution. Okay? And so that's kind of what that's showing you. And I mean, you can maybe imagine the reason for that. As you add more energy into something, at any given point, you're going to have a lot of particles that are going faster now, but then you're also going to have some particles that lose their energy as they slam into other particles and then transfer most of that energy to something else. Okay? But on average, this U right here represents molecular speed. Okay? All right. Effusion. Did we talk about effusion and diffusion last year? I really can't remember. Effusion is easy. It's just the best thing to think about with diffusion is probably a balloon. Let me see if I have a picture of a balloon. No. You see how there's a tiny hole right here? Okay. The gas effuses. It's going through a tiny hole in its container. Okay. A balloon has a bunch of tiny holes. Okay. The latex actually has tiny microscopic holes in it that these gases can eventually squeeze their way through and get out into the atmosphere. So that's why a balloon, a latex balloon especially, just a normal balloon that you would blow up, it deflates fairly rapidly even if you tie it off and there's not a noticeable hole in it. Okay? And they will deflate faster if they have helium in them.
If you're in the building, can you please call the activities office? 26239.
Okay. They'll deflate faster if they have helium in them than they will if they have oxygen or nitrogen in them.
Dale Sanders, it's all a go. You're okay.
That was a cryptic message. All right. Anyway. So that's effusion. Okay. Effusion is, just think balloon or, a gas escaping from a tiny hole in its container. Okay. Diffusion, you're not really talking about a container necessarily. You're just talking about there's a high concentration of gas in one part of a room, maybe, and it starts to gradually spread out to the rest of the room, okay? Something like that. So it's not really squeezing through a tiny hole. It's just spreading out, okay? I'm not sure what this picture is supposed to be here. I really can't tell. But they're timing something, evidently. A good example of diffusion.
Ruthie Yunt, please call the main office. Ruthie Yunt, 26226. 26226, thanks.
Okay. A good example of diffusion would be like spraying perfume or cologne on one side of a room, and then after a couple minutes, everybody can smell it because those molecules have kind of spread out everywhere, right? Okay. So that's diffusion. Did we? Okay. Yeah, that's right. Yeah. Okay. So, in the real world, behavior of gases only conforms to... Oh, wait. Whoa. We seem to have just gone through everything. Because this is 10.9 when we start talking about real gases. Is that really all I need to talk about? That can't be right. Hang on. I'm going to check the books. I knew it was going to be a short video. I didn't know it was going to be that short. But the thing is... Yeah, I mean, that's pretty much it right there. Yeah, I don't know that we need to talk about anything else here. There are a couple of equations in these two sections in the book, but what I actually told you on your reading guide is you don't need to know the equations. What I do wish I had was a couple of practice problems, because here's the kind of thing that you might see on an AP exam. They might ask you, which of these gases diffuses faster? And they might say, maybe they would even say helium gas or nitrogen gas, nitrogen gas, you know. I can't talk and write at the same time. Okay? So which one of those would diffuse or effuse faster? Okay? And the answer to that would be, and why helium? Okay. Effusion kind of makes sense, right?
Attention everyone in the building. We have servicemen here working on our heating and air conditioning units.
Sorry,
the alarm may or may not go off.
Wonderful.
Please ignore. We are safe.
So we
What?
we are safe. We may get a fire alarm in the middle of this video. Now I better end this fast. This is not a good video. The only reason it's been 10 minutes so far is because there's been 5 minutes worth of announcements. So helium or nitrogen, you can kind of imagine with diffusion it makes sense, right? If a gas is trying to squeeze through a tiny hole in its container, the smaller gas is probably going to squeeze through faster, right? Does that make sense? So if I'm asking which one of these would effuse out of a balloon faster, then that's fairly obvious. If I'm just asking which one is going to diffuse across a room faster, helium or nitrogen, that's maybe a little bit harder. But there is a very specific answer to this, and it comes from, well, I call it the big dog, little dog thing. Did I tell you guys the big dog, little dog scenario last year? We must have talked about this at least a little bit, because I feel like I told you guys this. But the big dog, little dog thing, if you have a little dog and you've ever watched it, you know, it eats a certain amount of food, it gets energy from that food, and then it zips all over the place, right? It doesn't take very much energy to get that dog moving in one direction or another, because there's not that much mass to get moving in the first place, right? Big dog, they can't do that. They can't zip around a living room like that. They have to get going a little bit. It takes them a while, okay? So give a little dog and a big dog the exact same amount of energy, and the little dog can do more with it. It can, and I say do more with it, it can move faster with that energy, okay? It's the same thing with a particle. So you give helium, small molecule, small atom, I guess, because it doesn't form molecules, but very small atom, you give that a certain amount of energy, it's going to move pretty fast. You give nitrogen, which is going to be N2 in its molecular form, right? That's quite a bit heavier, so you give it the same amount of energy, and it can't move quite as fast with that amount of energy, okay? So if you want to talk about given the same amount of energy, which one of these particles is going to move faster, the helium is going to move faster than the nitrogen, okay? And it's just based on their size. All right? Anything else we need to talk about? I think that's really pretty much it. If you can figure out which one is moving faster, then you can figure out which one is going to diffuse or effuse faster. Okay, it's just kind of a natural consequence of that. All right, I think that's pretty much it. So the bulk of the practice problems you guys are going to be working on tomorrow are probably going to be the ones that I gave you today, because the stuff for tomorrow I don't think is going to be that bad. But I'll make sure there's answer keys for all of that, and hopefully you guys will be fine. You'll be fine. You'll be fine. I'm still rambling. I'm going to end this video.